Hi, in this video we are talking about the story how Spider-Man defeats Spider-Man, or how we break the Bitstream encryption engine using the Bitstream encryption engine. So we found a vulnerability against the Xilinx 7 series FPGAs, which enables us to decrypt and manipulate its bitstreams. So this video is all about how the attack works, and at the end we also look on possible countermeasures against this unpatchable attack. My name is Maik and I'm one of the co-authors of the corresponding paper. Here we have a Basis 3 board, and here in the middle there is this tiny IC. This is an FPGA. FPGAs are fairly special ICs, so they can become any digital circuit you want it to become. So thinking on all these gates, these NANDs, NORs and so on, and you can really program each Boolean gate here on. So they are fairly cool. And to program this FPGA here, you use a so-called bitstream. And this bitstream contains all the vital information to program this digital circuit onto this FPGA. So it basically is the firmware of the FPGA stream. And the bitstream you can load it by USB, JTAG, and here on the back there is an external memory, and you can flash this external memory. So and when an attacker gains access to this bitstream, for example here on the external memory, they can easily read it out. They can gain access to all the vital information inside the bitstream. So all the intellectual property, the algorithms and so on. FPGAs are reprogrammable, and the flash is also reprogrammable. You can manipulate the bitstream. And so you can implant hardware trojans inside your design. So all the vendors came up with the bitstream encryption. So they store on the external memory the bitstream encrypted. And when you program the FPGA itself decrypts this encrypted bitstream and also ensures the authenticity of the bitstream. What we are going to do is we attack this. We read out the encrypted bitstream, for example, from this external memory, and then manipulate this to ask the FPGA to decrypt the encrypted bitstream for us. So we use this Spider-Man inside here to defeat the Spider-Man inside here. So we use it as an oracle basically. And in a second attack, we also can manipulate this encrypted bitstream. So we can implant hardware trojans. So let's take a look inside the attack and how it works. Before we go more into detail, let's first program this FPGA to see how this bitstream actually works. So here we have the FPGA and the bitstream containing the design, which we load to the FPGA via a programming port. So here, for example, the JTAG. And this programs the so-called fabric where all the FPGA magic happens. So here the reconfigurable routing and the lookup tables, and so everything is placed here. And there is a small tiny part beside this fabric which oversees this configuration process, and we call this the configuration engine. And this configuration engine comprises about 20 documented registers which the bitstream is reading and writing to. So the bitstream contains commands to read and write to these registers. And as we are here in the crypto domain, we need a decryption core for the encrypted bitstream. And we place this in front of the configuration engine so that the bitstream can be decrypted on the fly, so that the configuration engine only sees decrypted content. Now let us program this example bitstream here to see how this programming actually works. And first, there is a header sent to this engine, which basically sets up some registers already. And then the start decryption command here start this decryption core. So now click, we switch on this decryption core. So now every part of the bitstream is routed through this core and decrypted on the fly. So the configuration engine only sees decrypted content now. And we also take a sneaky look inside this encrypted bitstream here. And the first command here is an HMAC header. And this HMAC ensures the authenticity of this bitstream, so we can't manipulate this bitstream. Then a write to the control 0 register writes the next word to this register. And this is how the commands actually work. So we have a command to write to a register, and then a number of words is written to this register. And then the write to the FDRI command actually writes all the fabric data now to the fabric. So all the next words are these valuable lookup tables, reconfigurable routing, all the design information are now written to the fabric. And this is where all the valuable IP are. And this is what we want to attack. So now we come to our first attack, to breaking the confidentiality. Okay, so here we are in the state right before we issuing this writing to the FDRI register command. And we manipulate this command to not write to the FDRI register, but writing to the WB star register instead. And we can just do so by exploiting the CBC malleability. Okay, so now let us issuing this command here, so that now the following words are not written to the fabric, but written to this WB star register. So now the WB star register holds the decrypted fabric data in a decrypted way. So they are the valuable plaintext data in this register. And then we just cut the bitstream to not write any more data to this register, but we still have to send this HMAC tag. And the FPGA checks then the authenticity, but obviously it fails as we have manipulated the bitstream. And so the FPGA resets itself as a security mechanism. And now here comes the trick of our attack. And therefore let us look inside the documentation, and I will read out the relevant part. So when a fallback happens, an internally generated pulse resets the entire configuration logic except for the dedicated multi-boot logic. So this warm boot start address register, this WB star register, is not reset. Okay, so here we are in the state right before the reset happens. And bam, everything is resetted except this WB star register. And this is the point. Now the WB star register holds the decrypted fabric content, and it's decrypted, so it's plaintext data now. And also the crypto core is resetted, so we can now use a readout bitstream just to issuing a readout command to read this WB star register, and so the FPGA leaks out the decrypted fabric data. So we use this bitstream encryption engine to break the bitstream encryption engine. Okay, so let's wrap up the attack. First, we have to manipulate the bitstream to divert the bitstream content to this WB star register. Then we have to configure the FPGA with this manipulated bitstream, which is then noticed by the FPGA, so it's resets itself. But we can then use the readout bitstream to read out the WB star register, and so leaking out one bitstream word, which is 32 bits. And then by resetting the FPGA again manually and repeating all those 5 steps, we can leak out the entire bitstream. So this was our first attack to break the confidentiality. And now with our second attack, we will break the authenticity of the bitstream, which was really straightforward, as the HMAC key is stored inside the bitstream header. So this HMAC header can be decrypted by our first attack, so we can gain access to this HMAC key and thus forge valid HMAC tags ourselves, and so breaking the authenticity. So what went wrong here, and what are the root causes of our 2 attacks? And first, we have the bitstream commands interpreted before they are validated by the HMAC. So this is a standard use before validation attack. And secondly, the HMAC key is stored inside the encrypted part, thus the key is dependent of this confidentiality. So when we broke this confidentiality, we also can break the authenticity. But what can we do against these attacks in particular, and what are more general defense techniques? So first, of course, there doesn't exist any countermeasures for the current 7 series, as the attack is already in the silicon, so it can't be patched.
but they exist raised bar countermeasures, so for example obfuscating the design or a PCB modification. But for the new series, they have a complete new Bitstream encryption engine, so they are actually validating the bitstream before they are using it, so countering this root cause here. But in a more general way, we remember that the flaw was already visible in the documentation, and this is how we also found this vulnerability, just by carefully reading the documentation. So one should prove this entire system by these model checking techniques, since the underlying algorithms like AES and HMAC hold their security once again. They are proven. And thus one would avoid these ad hoc security designs just by proving the whole system design. Of course, another way to improve the overall system security is by letting the community reviewing the design. Since years, this is done in the crypto community as we follow Kerckhoffs's principle, so when a new algorithm comes out, the whole community tries to prove and to attack this algorithm. Yeah, what we have shown here is the full break of the Xilinx 7 series Bitstream encryption. Thank you very much for your attention so far, and I hope you have a lot of questions which we can discuss on all the various channels.